Hello everyone. In this lecture, we are going to see about filters, oscillators and mixers in RF transceivers. Objectives of this unit is to apply knowledge to identify a suitable architecture and systematically design an RF system. Then able to verify the basic principles and design aspects involved in RF system components. Next, resonator. In RF transceiver, a basic resonator is used to generate and stabilize the desired frequency of operation. In the field of electronics, a basic electronic resonator can be a simple LC circuit. It is also known as a tank circuit. The combination of inductor and capacitor creates a resonance circuit that can store and release energy at a specific frequency. There are many types of resonators are available. One is crystal resonator, ceramic resonator, surface acoustic wave resonator, dielectric resonator, coaxial resonator and microstrip resonator. These are some of the common types of examples of resonators used in RF transceivers. The choice of resonator depends on factors such as frequency range, stability requirements, size constraints, and cost considerations. The different resonators offer different advantages and are selected based on specific needs of the transceiver design. Next, filters. In RF transceivers, filters are essential components used to manipulate the frequency spectrum of signals. They help in separating or combining different frequency bands, attenuating unwanted signals, and enhancing the desired signal quality. There are 4 types of filters are available: low pass filter, high pass filter, band pass filter and band stop filter. First, low pass filter. It allows frequencies below a certain cutoff frequency to pass through while attenuating higher frequencies. They help in to remove unwanted harmonics and noise from the transmitted or received signals. This is the magnitude characteristics of a low pass filter. Then high pass filter. It allows frequencies above a certain cutoff frequency to pass through while attenuating lower frequencies. It is also used to eliminate DC offset or low frequency interference from the signal. This is the magnitude characteristics of high pass filter. Then band pass filter. It allows a specific range of frequencies to pass through while attenuating frequencies outside that range. It is used to select a particular frequency band of interest and reject unwanted frequencies. This is the magnitude characteristics of band pass filter. And last, band stop filter. A band stop filter is also known as notch filter. It attenuates a specific frequency band while allowing other frequencies to pass through it. It is useful for eliminating interference from a particular frequency or removing a specific narrowband noise source. This is the magnitude characteristics of band stop filter. Next, we will see special filter realizations. There are 2 types of special filter realization. First one is flat butterworth filter realization. Second one, equiripple Chebyshev filter realization. Let us see one of the realization. First one, flat butterworth filter realization. A butterworth filter is a type of electronic filter used to selectively pass or reject certain frequencies in a signal. It is a type of analog filter. The term flat refers to its magnitude response in the passband, which is designed to be as a flat and even as possible. Within its passband, the filter has a flat frequency response and does not introduce any ripples. Next, we will see the design of Butterworth low-pass filter. The design of Butterworth filters involving selecting the filter order, that means determines the sharpness of the roll-off, and the cutoff frequency, that means the frequency at which the filter begins to attenuate the signals. Higher order Butterworth filters can achieve steeper roll-offs at the expense of greater complexity in the filter design. Let us see the design of Butterworth low-pass filter in RF. We need to consider two parameters as an important thing. One is insertion loss. Insertion loss is an essential parameter in RF systems as it directly affects the overall signal performance. It refers to the amount of signal power lost when a signal passes through a specific component such as cable, connector, filter, amplifier, or any other RF devices. Insertion loss is typically expressed in decibels. That insertion loss is denoted as IL. IL equal to 10 log of LF. LF denotes loss factor. It is equal to 10 log of 1 plus A square into ohm power 2n, where IL is the insertion loss, LF is a loss factor, A is a constant, and ohm is the normalized frequency, and it is equivalent to omega divided by omega c. Omega divided by omega c a frequency component. N, it is the order of filter. Let us assume A equal to 1 and ohm equal to 1. We'll get this equation like IL is equal to 10 log of 2. It is equivalent to 3 dB. Next, insertion loss versus normalized frequency. The graph shows the representation of insertion loss versus normalized frequency. The insertion loss versus normalized frequency plot is an essential tool for filter design and performance evaluation. It allows engineers to assess the filter's behavior across a wide frequency range and determine its suitability for specific applications. In this graph, at the normalized frequency is equal to 1, that means cutoff frequency is equal to 1. After that, we will be getting insertion loss. You are increasing order of filter, then the insertion loss is also increased. Let us see the realization of Butterworth filter. The figure shows one common type of realization of Butterworth low-pass filter. Initially, we set Rg equal to G0 equal to 1. The element values in the circuits in a figure are numbered from G0 at the generator side, this is G0, and Gn plus 1 at load location. The elements in the circuit alternate between series inductance and shunt capacitance. From this figure, Rg equal to G0 equal to 1, it is an internal generator resistance. Gn plus 1 is the load resistance if the last element is shunt capacitor. Then Gm, it is an inductance for series inductor. The M value goes to 1 to up to N. N is the order of filter. The table shows the coefficients for maximally flat low-pass filter. for the filter order n is equal to 1 to 10. The table consists of the G values, that is G elements connected in that realization. The G values based on G naught equal to 1 and the cutoff frequency omega C equal to 1 for the filter of order n is equal to 1 to 10. Next, the one more important parameter involved in the filter design, that is attenuation. The attenuation in Butterworth filters refers to how much the filter suppresses or reduces the amplitude of a certain frequencies in the stop band relative to the pass band. It is a measure of how effectively the filter can remove unwanted frequencies beyond the cutoff frequency. In a Butterworth filter, the attenuation in stop band increases with the filter's order. The corresponding attenuation versus normalized frequency for various filter order is shown in figure. As we know that normalized frequency, that's ohm equal to 1, is the 3 dB cutoff frequency point. The attenuation curves shown in figure are very useful in determining the required order of filter. From figure, for instance, if a maximally flat low-pass filter is to be designed with the attenuation of 60 dB at the normalized frequency ohm is equal to 2, we see that the order of n equal to 10 of a filter is required to achieve this condition.